Hello and welcome back. Today I am excited to show you something really cool I managed to do with my 5-axis printer. Check out this print you are seeing right now. It took a ton of work to get to this point, and I hit so many problems along the way. Some I anticipated, but others were completely unexpected. This journey has been a fantastic learning experience for me, and I hope to share some of that knowledge with you. I am thrilled to showcase this because there were many moments over the past few months where I thought I hit unmovable roadblocks. But with some creative ideas I managed to solve or at least work around them until I find a better solution. As I progress, I keep gaining confidence that this will eventually work and be able to print useful models, not just gimmicks and abstract things. I think we are all wondering the same thing at this point. Why isn't there a commercial product like this? Well, there are indeed 5-axis 3D printers on the market, but they are not hobby grade. They are more like full-stack professional platforms, combining specialized software and hardware. Initially, I expected this project to demonstrate why these printers are inaccessible due to issues with accuracy, rigidity, and costs. However, I felt compelled to give it a try anyways. Now, as I get closer to my end goal and I can see the light at the end of the tunnel, I am starting to believe all those potential problems can indeed be resolved. Even with a printer made mostly of plastic and aluminum, it seems feasible. In the past, I've spent countless hours watching YouTube videos of people building 3, 5 and 6-axis CNC machines. The first thing you notice about those builds is that they are designed with extreme precision and sturdy materials. I thought this would be the main reason why we can achieve the same results with cheap off-the-shelf 3D printing gear from places like AliExpress. I imagine that precision could be the issue impossible to fix with the materials we use. So the question was, can I overcome those problems? Stay tuned if you want to learn what I found out. But before we begin, special thanks to the sponsor of this video, LGU. They reached out and sent me the brand new Mars 5 Ultra resin printer. I was already a customer and had a Saturn II which I was planning to use, but this one is even better. It features a 9K 7-inch monochrome LCD screen that precisely masks UV light to cure resin layer by layer, ensuring detailed prints. This high-detail screen provides XY resolution of 18 micrometers, meaning each pixel is only 18 micrometers in size. This fine detail results in smooth surfaces and sharp edges on your prints, accurately capturing even intricate designs. The Wi-Fi connectivity allows for remote monitoring and control, making it super convenient to start, pause or stop prints from anywhere. The built-in camera adds an extra layer of convenience, enabling you to keep an eye on your prints in real time and even create time-lapse videos to share your printing process. One of the standout features is the tilting printing platform, which tilts between layers instead of just pulling straight up. This significantly reduces the risk of print failures by minimizing the forces on the print during layer changes. Additionally, the platform features an easy release mechanism that makes removing finished prints effortless. Combined with other reliability features like a robust Z-axis rail system and improved cooling, it ensures consistent, high-quality prints. It was a delight to use. In this video, I also want to explore the role of resin printers in projects like this, which is mostly mechanical. Throughout the video, I will show you some use cases where I think resin outshines plastic. Also, a huge thank to my patrons for supporting my work. I am thrilled to see the community engagement on the channel, in the comments and with your ideas. I always read the comment section and some of you have shared fantastic ideas and solutions I couldn't have thought on my own. But for now, let's go through the hurdles I managed to overcome in the past month or so. For starters, let me confess something. It's one thing to make 5-axis print with continuous movement of the new axis, like I did before. In that scenario, precision isn't as crucial. If there are imperfections in alignment of the planes and axes, those inaccuracies will be absorbed progressively by each tiny layer change. Of course, the models could be slightly distorted, but they won't fail at least. That wasn't my end goal here. What I envision is getting a slicer to redefine the plane at which the slicing is done. This means using the A and C axes to change orientations when it's convenient, then continuing to extrude upwards in the traditional manner. I think by doing this, we can reap some of the potential benefits of a printer with these characteristics. On one hand, we can redefine the planes to maximize the part's strength or avoid using support material. On the other, the change in slicing software should be easier to achieve. This idea, as I expected, opened a can of worms. As you can imagine, even a minor change in the angle of rotation of the A or C axis can significantly affect the position of the tool head relative to the printed part. If the alignments aren't perfect, the entire piece could be either missed or crushed by the nozzle. The solution is to improve the precision to ensure that even with significant movements in the A or C axis, the printer can still position the tool head precisely where it's expected. To achieve this, I devised a series of algorithms in Clipper and printed tools. The main goal of this video is to walk you through the alignment routines and the tools they use. Let's begin by talking about alignment and the problems of not having good alignment more precisely. Imagine a scenario where I have a figure I want to print from the bottom up, then I want to rotate it some degrees and continue printing on a new plane based on the shape I'm trying to achieve. Let's say there is a small misalignment in the A-axis. For example, the A-axis thinks it's at 0 degrees, or the bottom position, but in reality is leaning to one side. Now imagine we rotate it 40 degrees and use math to position the print head on top of the new surface. If those 40 degrees are off by just 1 degree, we can quickly realize that after the rotation the figure will be either some millimeters above or below the expected position. Given that our layer height is most likely around 0.2 millimeters, that inaccuracy will be impossible to bridge with the material we are extruding. At that point, the entire print will fail, resulting in either a crash on the part or a lot of spaghetti to deal with. Now, let's identify the axes and planes that we crucially need to align with each other and figure out how to address that alignment. The A-axis needs to be parallel and aligned to the X-axis. To achieve that, the Z-axis must be perfectly calibrated. If one of the Z motors is higher than the other, we will get a tilt. Also, as the tool head moves along the X-axis, it should follow the A-axis parallelly. The A-axis dead bottom needs to be perfectly calibrated. This means that when I rotate A to plus 90 or minus 90 degrees, the tool head should be able to find the rotational base at the same Z height. Next, we have the Z-axis, which is crucial to calibrate. Initially, I almost missed part of its calibration. The Z-axis should pass perfectly through the 0, 0 position of X and Y at any given Z height. If that's off, the rotations of Z will throw everything out of whack. Once Z is aligned with the origin, we need to ensure it's also perpendicular to the plane formed by X and Y. If not, we face variations of the problems mentioned earlier. For all those aspects, I devised a way to align them. Against all odds, it seems to be working quite well. Believe me, I was just as surprised as you are that all of this is actually functioning. The solution was achieved by using the 3D probe I designed and talked so much about before. If you remember from my previous videos, I mentioned wanting a toolhead that can probe X, Y and Z. The reason for that may not have been clear back then, but it will be obvious after I show it in action. To get it working this way, I had to modify Clipper's code. Normal 3D printer probes were just in the Z-axis and downwards, using the probe command. I wanted to be able to specify in the command how to probe, including which axis and direction. This requires some changes on the code, which you can find in my link to my GitHub in the description. I eventually ended up with a probe command that accepts two new optional parameters, axis and direction. Additionally, I added some more commands for calibration and a function to find the center of a hole, which proved quite handy for the calibration process. Needless to say, my probe does work, but lacks precision. It has an accuracy range of 0.5 to 1 mm, which is significant in this context. I need to reduce that to around 0.1 mm at the very least. I am already working on that, but my priority was to develop the routines that will leverage the probe. At the end of the day, I want to see if my ideas work before spending dozens of hours on a mechanism that may not be helpful anyways. So I used this imprecise probe as best as I could and developed the algorithms. Now that I've proven the concept to be feasible, I will focus on improving this piece of hardware. I think taking baby steps is the way to go here. And since we are talking about precision, this is the first use for resin I will bring up. I mentioned finding holes, and the rounder those holes are, the better for calibration. Compare this. FDM printers do an okay job, but those holes aren't truly round. Now compare that with the ones produced by resin when printed in the correct orientation. See the difference? We need to reduce the inaccuracies to the bare minimum if we want to succeed here. So, thinking ahead, I ended up making my calibration tools out of resin instead of ABS plastic. I still use the plastic bits while developing the routines because they are easy to reprint and replace during the inevitable crashes. but once I was comfortable with the setup, I swiftly replaced them with the final ones made on my Mars 5 Ultra printer. At plain sight, you can't even see the layers at all. For the calibration routines, I modified Clipper's Python code. Initially, I intended to create macros in the config file, but I quickly moved past that idea. Macros aren't nearly as powerful as Python, and don't have access to all the values and functions I needed. So why bother with macros when I have access to a fully fledged programming language that I am already tinkering with anyways? So, for calibration purposes, I created the following tools. Notice that the upper hole is aligned with the A-axis of rotation. By finding the center of it, we are effectively finding points alongside that axis, which will simplify the math for calculating the deviation of the angle of A later on. Both tools have a secondary hole 50mm by 50mm apart. All 4 holes belong to this plane as well, which will be useful for the calculations. You may wonder why the calibration tool on the right is so bulky and awkward. The reason is that the strictly symmetrical tool can't be reached by the nozzle tip due to the size of the carriage. The problem with using those tools is that I need to install them for calibration, but I have to remove them to print to avoid collisions. Not to mention the dramatic reduction in print volume if I try to print with them installed. It's a bit of a pain. And I wish I could leave them installed without any setbacks, but for now I can't see how to get both requirements to coexist. Another advantage of using resin instead of plastic is that if I am executing the routines with the nozzle at high temperature, the resin won't melt or deform as easily. However, this shouldn't be attempted regardless. My intention is to run the calibration when the printer is cold. Lastly, before we start going through the actual calibration routines, notice how I made them output a lot of information in the console. I am displaying details about the probed positions and the calculated differences that the machine will try to compensate for. Some of those values can be used to fine-tune the parameters in the configuration. That, in fact, is the end goal. We don't want to waste time running these routines constantly or even before every print. Ideally, the printer gets calibrated and configured properly once, and then a simple homing sequence should take the nozzle to the right spot. In reality, I have executed those routines probably hundreds of times while developing them. I have also had to run them after crashes or even after moving the frame around. Remember, the materials are quite soft and things can shift. If anything moves even by 1mm or if a stepper motor shifts slightly with respect to the others while the printer is off, then the calibration needs to be done all over again. Finding the hole's center is straightforward. First, I need to place a tip inside the hole. Precision isn't crucial here, just a rough estimation will suffice. Then I probe upwards in the y-axis and downwards. The difference between those positions divided by 2 gives the center of the hole in y. I repeat the process for the x-axis. Probe right, then left, and divide the difference to find the center of the hole in x. This brings me to another scenario where I choose resin over plastic. Organic shapes. In a previous video, I added a screen to my printer, which was instrumental in working on this part comfortably while trying to find those starting points. While developing the calibration routines, I had to manually position the nozzle at some relevant spots, and having the screen right at my fingertips was incredibly useful. The screen uses a case I designed, which is rounded and organic. You could print that with FDM printers, but the quality is rather poor. The resin printer does a much better job with those parts. Yes, this is a vanity use case, but it's worth mentioning regardless. As for the rough places where the tool's holes are, I've hard-coded them in the calibration routines for now, but I will eventually move them into a new section in the config file. With that said, let's walk through the calibration routines one by one. First, the simpler one, leveling both Z motors' height. I relied on the calibration tools because the nozzle tip can't reach the right side of the rotational platform any other way. So I selected a flat surface and probed the top, first on one side, then the other. Once that difference was calculated, the second motor moved independently to compensate for any discrepancy. That was simple enough. Now let's talk about the calibration of the rotational axis A. First, the parallelism of A with X doesn't seem to be a problem. I used a little spacer tool in the past to position the Z rails, and that seems to have done a good enough job, so that wasn't an issue that required my immediate attention. Similarly, the vertical alignment of A was already achieved by calibrating the Z motors to be level. So we only need to deal with the dead bottom situation. Here is where the 4 holes in the calibration tool came in handy. Since the secondary holes are 50 mm below the first ones, and the first ones pass exactly through the rotational A-axis, we can use simple trigonometry to determine how crooked the A-plane is. Once that parameter is identified, A is rotated in the opposite direction to compensate. The value is displayed on the console, so I can plug it into the configuration, and the same process is repeated on the right side. The only difference is that the rotation compensating the left side moves both motors simultaneously, while the compensation calculated for the right motor affects only that one. This evens them out. Additionally, by finding the center of those holes, I can now obtain the exact position of the nozzle concerning the Y-axis, which I can use in my configuration to fine-tune the Y end-stop position. Once the configuration is updated to reflect that, the Y position at 0 should pass exactly through the A-axis. I can verify that this process works as expected because I can execute the calibration command twice and should see less compensation each time. Needless to say, due to the inaccuracies of the probe, there is always a very small movement. I can't wait to have the probe working as I envisioned, so all those routines work flawlessly. The last important routine I worked on was designed to find the exact center of the printing heatbed, which should also be a point that passes through the C-axis. Initially, I planned to use the 2 holes I designed in the printbed PCB, but I realized they weren't necessary, and the next iteration of the platform won't need them. It's enough to measure the position of the heatbed on the left and then on the right, calculating the center with basic math. This is quite similar to finding the center of a hole, except this time the measurement is done on the outside of the figure, not inside. That center point will be where x should be 0. I took note of that difference and plugged it into the configuration's x end-stop position to ensure proper calibration after the next homing runs. Next, this routine measures the top of the printbed twice, at 2 points some distance apart on the x-axis. If the line described by those points is not perpendicular to the x-axis, the heatbed is rotated to compensate. In hindsight, I don't really need to do that. Even if the heatbed is not perfectly square, it shouldn't affect the prints. In fact, the next time I make a heatbed for this printer, I will probably make it circular with no holes. Finally, during this routine, I take a final measurement of the set position at the center of the printbed. Then go back to measure the top of the first calibration tool. This difference is a crucial value that I will need to use eventually during slicing. That height will be used to compensate Y when rotating A. For example, if I rotate A by 45 degrees, then Y should be moved as well to stay on top of the shape I am printing. And then I thought I was done with the alignments and started working on the model I wanted to print. It's this kind of ugly propeller that has no real use, but is a good example of what we can do with this printer. However, I ran into a couple more issues before I could get the machine to print what I wanted. I discovered those problems when I tried to print the sample model. As a side note, let me show you another scenario for using resin, transparent material. I had previously added LED strips to improve the lighting for my videos, but I did a really poor job installing them, and now they are falling off. So I designed a case for them and printed it in transparent resin, and they look terrific. I know transparent PLA exists, but for this I usually choose resin. To explain the rest of the problems I ran into, I first need to explain my plan for printing in 5 axes. My strategy was to create 2 individual G-code files with Cura. One for the base of this propeller I designed and another for the propeller blades. I sliced the base and then added some extra G-code at the end of that file, designed to rotate A and compensate Y and Z for that rotation. Afterwards, I appended the G-code of the second slice file. This manually added G-code should rely solely on maths, otherwise it wouldn't be a good proof of concept for the changes I am planning to make in the slicer. My idea is that every piece of G-code should either come from a slicer or be derived from the math of the rotations. Nothing should be eyeballed or guessed by human observation when creating the G-code. If I do that, it becomes a gimmick and not a truly useful proof of concept. Although that plan eventually did work, it didn't come without its challenges. While trying to achieve this, I learned something that threw off my plans. All the slicers we use, including Cura, use absolute positioning. I thought they could be configured to use relative positioning. The difference is that in absolute positioning, the instructions in the G-code file specify distances always calculated from the origin. With relative positioning, the commands in the G-code file could instruct the machine to move a certain number of units from the current position. Well, it seems that doing so is not possible or advisable. Slicers don't provide that option. My understanding is that it has to do with consistency and accuracy. In absolute positioning, every movement is based on a fixed coordinate system, which minimizes the accumulation of errors. In relative positioning, small errors can compound over time, leading to significant discrepancies in the final print. This is where I found a clipper command that came to my rescue. It allows me to set an offset for the nozzle. This is not what I initially wanted because I am injecting clippers commands in the middle of my G-code to compensate for something I cannot do otherwise. Alternatively, I could have created a script to post-process the second slice file to shift all the positions to the new place after the rotation. Keep in mind this was just a proof of concept to see if the idea was feasible, not a proposal for practical slicing method moving forward. That would be an absolute pain. The idea was to concatenate two G-code files and add some G-code in between to change the main plane. If this worked, I could potentially make this change programmatically in an existing open source slicer. But first, I had to test the feasibility of such an idea. As you can see, my initial assumption was wrong, so imagine making such a change in a slicer only to discover the absolute positioning issue. Now I can keep this in mind while implementing changes in a slicer. I am glad this happened now, it saved me time and pain in the future. At this point, I had a G-code that had the potential to work, but when I tried it, the planes were misaligned for some reason. After the rotation, the nozzle was always a few millimeters off the mark. I knew the math was correct, and I had implemented a workaround with the offset. It had to be a missing alignment I hadn't accounted for or something else. It turned out to be due to two problems. First, remember the layer shift I was experiencing, which I reduced by increasing the microsteps. This problem persisted, though very slightly, so I couldn't see it with the naked eye. The almost insignificant layer shift was enough to throw my calculations off by a few millimeters. So it was time to fix that problem for good. Fortunately, I received some comments on the video where I mentioned the issue, and some of you hit the nail in the head. The problem was that my stepper controllers needed a small step pulse duration to work properly. Clipper supports that parameter in the config. With that set up properly, the layer shift fully disappeared, and I could reduce the microsteps as much as I wanted with no layer shift. As you can see, I'm slowly but surely paying my technical debt. That was the first reason why my calculations after changing the printing plane didn't match the printed model, but there was still a second problem. After banging my head for a bit, I realized I was still lacking some calibrations of the Z-axis. Despite all the previous calibrations, I failed to notice that the Z-axis was slightly tilted to the left. This one almost broke me. Initially, I couldn't imagine a good way of calibrating it. Eventually, I came up with the solution you see here. The rotating base where the Z-axis turns was redesigned to allow for manual fine-tuning. It allows for a small amount of tilt, which is all I should need, no more than a degree or two. By identifying the correct position, I could regulate it manually. In all honesty, I thought this attempt was gonna be fruitless. I didn't see how a manual calibration with bolts and nuts could ever be precise enough. My probe wasn't going to help me in this scenario either. I wished I had some way to project the axis upwards somehow. Eventually, it came to me. I printed yet another little tool that acts as a pointer, which I used to align the nozzle tip as precisely as manual tuning allowed. To my surprise, this approach did the trick. Look at this footage of me aligning the tips. It's probably not the best solution in the long run, but it's good enough for now. Now, this is what I managed to achieve. This is a great step in my opinion. I now know I can calibrate the printer as required and have a good idea of the kind of changes needed in a slicer to make this machine truly useful. Additionally, it validates my idea of using a 3D probe combined with the nozzle. Despite its current imprecision, the concept is sound. So, what are the next steps? I have two main goals in mind. The first is to improve the 3D probe. It needs to be better and more precise, without affecting the print quality due to the added hardware. This will be my last improvement on the mechanical parts. What I truly want to do is start working on a plugin or a slicer to properly slice in 5 axes. I am looking forward to working with the software since that's the problem I am most eager to address. I still have no idea where to start with modifying a slicer, but I will figure it out. As a last comment, I want to show you the final calibration I still need to do. If you look closely at this model, you will notice that the propeller blades are leaning to one side. This seems to be due to the alignment of X and Y axes. They are not as perpendicular as they should be. In a core XY setup, you can adjust the alignment by pulling more from one motor or the other. There is some imperfection in this printer that I need to address. This is a good example of how crucial it is to have perfect alignment and the consequences of not having it. I just wanted to show it as a sample of what could go wrong. All in all, I think I am really close to the goal I set for myself. I want to say thanks to Elego and my patrons for supporting my work on this printer. If you feel I'm doing something worthwhile and want to help support the channel and the project, please find the link in the description. Don't forget to subscribe and share, and thanks a lot for watching until the very end. See you next time.